Good afternoon. My name is Colin Eckel, and today we are going to talk about essential monitoring for quickly identifying and repairing air and leak sources. Intek has been involved in evaluating condenser performance and design for nearly 30 years and is the recognized leader in the field with numerous published papers and patents on measuring and improving condenser performance. The first thing I want to talk about is the effect of air and leakage on condenser performance. Air and leak is an ever-present issue for steam surface condensers, but it does not always cause a reduction in condenser performance or an increase in condenser back pressure. There are two distinct ways in which air collects in the condenser. The first is called a stagnant zone. This is air that collects at the mouth of the air removal section and is the result of the air and leakage being higher than the exhauster's capacity to remove it. As a result, the condenser pressure must increase to a point where the exhauster is now able to remove the air in an equilibrium state. A stagnant zone can be caused from an increase in air and leakage from some baseline value or a reduction in the exhauster performance. The key there is to know whether air and leak or degraded exhauster capacity is the cause of the problem. When a stagnant zone is present, there is an area of increased partial pressure of air. Air acts as an insulating blanket around the tubes, inhibiting heat transfer to the cooling water, resulting in colder tubes in that area. In addition, condensate falling through this area will drop in temperature and pick up dissolved gases like oxygen and carbon dioxide. These dissolved gases may not be pulled out of the condensate before it falls into the hot well, where they can remain trapped. Carbon dioxide is a small percentage of the partial pressure present in these zones, but additional chemical reactions can allow for carbonates and bicarbonates to be produced in the condensate. So the zone of high partial pressure essentially reduces the overall surface area of the tubes, contributing to excess condenser pressure, and may introduce dissolved oxygen and other compounds in the condensate. The other type of air storage is called an air-bound zone. It has all the same negative effects, but it is caused by condenser design or configuration. These zones are always present, even with minimal air and leakage. Not all condenser designs have air-bound zones, but most of the condensers I have instrumented and analyzed do. One of the services we have developed is the direct measurement of air storage. We install hundreds of temperature sensors inside the condenser to measure the real-time heat transfer of tube bundles. On the next couple of slides, I'll show you real measurements of these different types of air storage. This first example is from a power generation facility that we worked with to identify the source of their poor condenser performance. It started with measuring the level of air and leakage using the Intek REEvac condenser monitor. In analyzing the performance data we gathered from the REEvac, we recognized that there were other factors affecting the performance that needed to be understood. One of these was the condenser cleanliness factor. This is a performance map developed by Intek that illustrates the tube bundle after it was fitted with hundreds of temperature sensors. Additional instrumentation was used to measure pressure and circulating water flow rate. These measurements are used to calculate cleanliness factor based on inlet temperature, condenser pressure, and circulating water flow rate. This is not computer modeling, but based on real-time direct measurements. The colors represent cleanliness factor calculated from these temperature sensors on the outlet of individual tubes. What we see here is a condenser that already has a generally low cleanliness factor across the bundle. The areas of the bundle that are yellow and orange equate to approximately 75 to 80% cleanliness factor. And this was found to be caused by tube ID fouling, such as scaling or biological growth. The cyan color at the mouth of the air removal section represents a low performing area of approximately 40% cleanliness factor caused by a small stagnant zone. The animation shows how the stagnant zone grows when a controlled air and leak is introduced into the condenser. As the air and leakage increases, you can see the blue region at the mouth of the air removal section grow and expand out into the tube bundle. The blue color represents a growing and increasing amount of air collecting there, with these areas reaching into the single digits of cleanliness factor. This is the stagnant zone, as defined in the previous slide, and shows the impact that air and leakage in excess of pump capacity has on condenser performance. Now let's take a look at a condenser that doesn't have this underlying 2x defouling and has a pronounced airbound zone. This example from another power generating facility shows a condenser with the air remover section on the left of the tube bundle over here. And unlike the previous unit, there was no baseline tube fouling found in this condenser. The major difference being this deep red represent hot temperatures at the peripheral of the tube bundle and a cleanliness factor of 100 to 120%. As you can see, in the area near the mouth of the air removal section, there's quite a bit of yellow and green areas representing 60 to 80% cleanliness factor. This is the stagnant zone area on this tube bundle design. The stagnant zone you can see stretch over to the right and connects to this blue pocket of tubes, which has approximately 25% cleanliness factor. This is an airbound zone, which means that these tubes are nearly shut off from steam reaching them. Intek has been able to show that this is typically the result of poor design of the condenser's air removal section. Now let's look at how this combination of a stagnant zone combined with the airbound zone behaves in the presence of an air leak. At the start of the animation, there is low air leakage. The pocket of cold tube develops regardless of the air leakage level. As air leakage increases, the stagnant zone grows and extends all the way over to the airbound zone, resulting in a large area of very poor performing condenser. Now let's take a look at a very large and common condenser design. This tube bundle arrangement is from a very large Westinghouse condenser with a tube bundle design that is very common. We have had the opportunity to instrument several condensers of this design or with very similar tube layouts. The diagram on the left shows the performance map for low air leakage, and the one on the right shows performance map for high air leakage. What is interesting on the left is the pattern of airbound zone below the center of the bundle where the air offtake pipe is. This smiley face pattern is typical for the air binding in the Westinghouse design. It is worth noting that before we ever had the chance to install temperature arrays on a Westinghouse, we would see tube plugging in this same shape during condenser inspections, which indicated that it was inherent to the design. We observed this particularly in units with copper-bearing tubes and as a result of ammonia grooving. As a side note, Intek has successfully retrofitted these styles of condensers to mitigate the design-related issue. The previous few slides are intended to highlight examples of how air storage in the condenser affect performance of individual tubes and large sections of tubes within the tube bundle. It is also important to note that almost no one has access to data that can identify and measure the impact of these airbound zones like the slides I've just shown you. But there is instrumentation that is very useful for troubleshooting condenser problems, particularly those related to air and leak, which is the focus of this presentation. Intek has implemented a process for air and leak detection and quantification that is superior to other techniques through the use of multiple instruments to perform the testing. These are the instruments that are used to measure problems with vacuum equipment capacity and monitor air and leak while doing a helium leak test. A REEVAC multi-sensor probe is installed in the condenser vent lines, which allows for overall monitoring of the vacuum system, as well as monitoring individual vent lines, which can help narrow down the location of possible air and leaks. The REEVAC instrument provides real-time values for air and leakage and exhauster capacity. This information provides an indication of when a stagnant zone is causing excess back pressure within the condenser. Using multiple REEVAC probes can also provide information on general leak locations, as well as immediate feedback when a leak is found and fixed. And here's the helium leak detector, located on the discharge of the exhauster system. The helium leak detection equipment provides positive identification of the specific leak location. It provides a qualitative indication on the size of the leak, whereas the REEVAC system provides a quantitative measurement of that air and leakage. With this essential instrumentation setup, we can very quickly quantify problems, find sources for degraded condenser performance, and quantify the performance improvement when leaks are identified and repaired. The REEVAC instrument provides several outputs related to condenser performance. But for our purposes in this presentation, I will highlight a few of the significant outputs used for leak detection. First and most importantly, it provides an absolute value for the total amount of air and leakage into the condenser from all sources. Next is the mass ratio, which is the ratio of water vapor to air mass flow. This is the parameter that can indicate if a stagnant zone is present, causing excess back pressure. The rule of thumb is a mass ratio above 3 indicates no stagnant zone is present. And if the mass ratio is below 1, then there is a significant stagnant zone present, indicating the need for a call to action. Now, as you recall, a stagnant zone is caused when the air and leak is above the exhauster capacity. The action then is to determine if your leak is high or your exhauster capacity is low. For liquid ring vacuum pumps, the volumetric flow rate output, or ACFM, is the re-evac output for pump capacity. This value can be used to trend the pump capacity over time or be compared to suction pressure at the pump. For steam jet air ejectors, the re-evac total mass flow is the parameter that is used to measure their capacity. The re-evac pressure output is an independent pressure measurement that can be used as an indicator of pump suction pressure. This can be used in conjunction with manufacturer pump curves, which are typically provided with dry air capacity versus pressure design curves to determine pump performance. Using this data, you can determine if the problem is excess air and leakage or degraded exhauster capacity. Now let's look at a few case studies where the re-evac instruments were used in conjunction with the leak detection equipment to measure and locate leaks. While not all leaks can be sealed when they are found, we are going to show a few where it was possible to not only identify the source of the leak, but also measure the impact of repairing it. The condenser shown here is a combined cycle unit. There is only one vent line. You can see the steam turbine exhausting to the side of the condenser here. The vent line runs across the top of the condenser over this way to a bank of 2 liquid ring vacuum pumps. Due to limitation on space and access to the lines, a single re-evac probe system was used. This meant that the search area could not be as easily localized. However, it is a much smaller condenser than a typical coal or nuclear unit, meaning that the entire unit could be checked with helium in one day. This is the plot of the data that was collected by the re-evac system during the testing. I'm going to take a minute to go over the layout of this plot since we will be looking at several of them. The plot line corresponds to the matching axis color. So when looking at specific plot lines such as air and leakage, you will need to look at the matching colored axis here in red for the corresponding numerical value. Upon arrival at this site, the unit was running with approximately 50 SCFM of air and leakage, and the mass ratio was well below 3. Using the helium leak equipment, a large leak was found and was able to be temporarily patched. The total air and leakage dropped by 30 SCFM, and the pressure dropped by approximately 0.2 of an inch. Following the leak fix, you can see the air and leakage change and the mass ratio is above 3, indicating that the stagnant zone has been removed from this condenser as a result of fixing that leak. The leak that was found and temporarily patched was on the hood spray pipe seen here. This happened to be a high vibration area, and several of the other units had started to show cracking on these hood sprays. This plant has 4 identical units, and the action taken was to replace this connection with a flex line. This leak accounted for 30 of the 50 total SCFM. This unit also had leaks at the expansion joint and surrounding a drains tank that accounted for the remaining 20 SCFM. The drains tanks at this plant have a history of issues due to high vibration and extreme temperature swings that have caused stress cracking in the tank bodies. The bottom line is that as a result of the testing we performed, this plant was able to mitigate 2 major sources of air and leak and avoid potential problems on multiple units because we were able to locate and quantify both sources, which turned out to be common issues on all of their units. This could not have been accomplished in such a short time without the use of the re-evac in conjunction with the helium detector. For our second case study, we have a condenser that has two air offtakes that combine into a common and run to a bank of pumps. The layout of the vent lines did not allow a re-evac probe to be installed in each vent line, so a probe was installed in the west vent line and another one in the common line. And this customer contacted us to determine the source of increased air and leakage following a maintenance outage. On this plot, air and leakage is red and mass ratio is the cyan. The west vent line readings are solid, air and leakage here, mass ratio here, and the common lines are the dashed lines, air and leakage and mass ratio. This unit also has a test grade instrument package installed, which includes RTDs, pressure sensors, and a total circulating water flow measurement used to calculate condenser performance or cleanliness factor in real time. So I have included cleanliness factor here in green and condenser pressure here in blue. Looking at the first half of the plot, you can see the total air and leakage is approximately 40 SCFM, and the air and leakage from the west vent line is 6 SCFM. So with just this data, we know the air and leak is primarily sourced on the east side of the condenser and lower in the condenser. We know that air and leakage that enters the steam space high in the condenser near the turbine will be more evenly dispersed in the steam space and therefore equally shared between the two offtakes. Knowing that the east vent line has a much higher air and leakage as indicated from the re-evac measurements, we were able to focus our search efforts on the east half and penetrations and piping lower on the condenser wall, which made the process of locating the sources of the leaks more efficient and faster. Armed with this information, during the leak audit using the helium leak detection equipment and tracing lines from the east side of the condenser, we found several uncapped pipes. It was discovered during the maintenance outage a few months prior, the extraction steam check valve shown here had the packing replaced with a different gland that no longer required drain lines. The now obsolete drain lines were not plugged, allowing approximately 30 SCFM into the condenser. Once they were identified, plant personnel were informed and they were capped. The impact on air and leak is shown on the next slide. Looking at the time when the leak was fixed, right here, in addition to the 30 SCFM drop in air and leakage, there was also a 3% increase in cleanliness factor as a direct result of finding and fixing that leak. This last case study is an Ingersoll Rand condenser. There are two condenser shells running at a common pressure. Each shell has two bundles, each with a dedicated air offtake line. This unit operates with 3 re-evac probes. One probe is installed in the common, and the other 2 probes they allow to be moved between the 4 other vent line locations. For this leak audit, a 4th probe was installed and the common probe was moved so that each vent line 1 through 4 could be monitored. This plot shows the air and leakage for all 4 vent lines, which are summed up to get the total unit air and leakage. The first half of the plot shows the conditions before the leak is located and repaired, including the amount of air and leakage being measured in each vent line. The total air and leakage is approximately 17 SCFM, with the majority of the air and leak contribution in the number 1 and number 4 vent lines, which accounted for 14 SCFM. The number 2 and number 3 vent lines show very low air and leakage. Based on the design of this condenser, the primary source for air and leakage in these 2 bundles would have to come from expansion joints or turbine seals, or from penetrations directly above the bundles on the water box side of the condensers, of which there were very few. So based on this data, we were able to conclude that there likely was very little leakage from turbine steam seals and expansion joints. This meant that the effort searching for leaks could be focused on penetrations in lines entering near the number 1 and number 4 bundles. Narrowing down the leak search area would have been impossible, leading to an arduous search process without having a probe installed in each of the vent lines. During the leak audit, a leak was found on a line that penetrated near the number 4 bundle. When the leak was fixed, you can see the air leakage drop specifically on the number 4 bundle greater than in any other bundle, and leaving a total air leakage of approximately 9 SCFM. The leak that was found was a sheared off pipe stub connected to a sight gauge on a feed water heater. This was not located in a well-traveled part of the plant and would not be noticeable without climbing a ladder to this specific platform. Plant personnel closed the valves around the sight gauge, and the air leakage immediately decreased to approximately 9 SCFM. After the leak was repaired and the total air leakage was dropped to 9 SCFM, you can see the mass ratio increase from 4 up to 9. Now, a mass ratio of 4 is still above the rule of thumb of 3, which means that there was no stagnant zone formation with the 17 SCFM of air leakage. Now, with the mass ratio at 9, the plant was running 2 pumps. Now they can turn off 1 pump and run with only 1 pump with no increase in condenser pressure. During this presentation, I've shown the essential instrumentation we use to identify and repair air leak sources. I've also shown how this instrumentation can be used to determine if the condenser problem is a vacuum equipment problem or an air leakage problem. Using case studies and data to show how this can be done quickly and efficiently and recover potential loss generation from high condenser pressure. If you have any further inquiries or questions, please contact Mitchell Morrison at mmorrison@intekflow.com. That's mmorrison@intekflow.com or 1-800-743-6822. Thank you.